Okay, today we're going to talk about the binomial distribution. Okay, the binomial distribution arises from experiments with repeated two-outcome trials. And people get a little confused when they think of two-outcome trials. They think of like heads or tails. Yes, that could be it, but that's not it. One of the outcomes is counted. Okay, so here's what I mean by that. When you have a binomial distribution, you either have success or failure. Those are your two outcome trials. Either something happens or it doesn't. So if you're flipping a coin and you want to get heads, you either get heads or you don't. Does that make sense? So the outcome that is counted is referred to the binomial random variable. Now, here are a couple examples. The first example, the number of left-handed persons in a sample of 200 unrelated people. So let's say I have 200 people and I want to see if we have left-handed people. So either they're left-handed or they're not. Okay? So left-handed or right-handed. That's two outcomes. The number of correct guesses out of 20 true or false questions when you randomly choose an answer. So either you get it correct or you get it wrong. There are two outcomes. And then the number of winning scratch-off lottery tickets when you purchase 15 of the same type. Now, some people are like, there's a whole bunch of different options for scratch-off lottery tickets. You could win the jackpot. You could win like $10. You could win a free ticket. The two outcomes are you win or you don't. Okay? So whatever they classify winning as, you win or you don't. So a binomial experiment, there can only be two outcomes on each trial of the experiment. That's the first rule. There can only be two outcomes. We call one a success and the other a failure. You win or you don't. You have it or you don't. The second rule is the experiment consists of n identical trials as described in condition 1. So whatever you're going to do, you have to do the same thing every time. You cannot make adjustments as you move along. The third part, the probability of success on any one trial is denoted by P. Okay, so we call success P. And it does not change from trial to trial. So we're saying like the probability of success, the probability that you're going to win, that's going to be called P. Note, the probability of failure is the complement of that, 1 minus that. Now notice 1 minus P, we will also refer to it as Q. You'll notice that P is success, 1 minus P is failure, but a lot of times I call it Q. So that's something you might want to notate there. That also does not change from trial to trial. The fourth rule, the trials are independent. So the second run does not affect the third run. Okay, they are all independent of one another. And number 5, the binomial random variable is the count of the number of successes in trials. Okay? So that's a lot of information, and that can be a little bit overwhelming. So let's talk about an example, and let's see if it counts as a binomial experiment. Okay? So on number 1, toss a coin 4 times and record the number of heads. Is the number of heads in 4 tosses a binomial random variable? Well, in order for it to be a binomial random variable, it has to meet these 5 requirements. So, the first requirement, there can only be 2 outcomes on each trial of the experiment. Are there 2 outcomes when you toss a coin? Yes. What is my success going to be? Yeah, my success is going to be heads, which means my failure is going to be what? Tails. So that works for the first rule. First rule, 2 outcomes. Yes, heads and tails. Success is heads, failure is tails. Now the second rule, the experiment consists of n identical trials as described in condition 1. So how many times are we tossing the coin? 4. And is it the same thing every time? Am I changing anything about it? No, I'm tossing the coin 4 times. So n is going to equal 4 here. N is going to equal 4. Okay? The third rule, the probability of success on any one trial is denoted by P and does not change from trial to trial. So we said the success was tossing a heads. What's the probability of getting heads when you toss a coin? 1/2, 50-50, right? So the probability of success is going to equal 0.5 or 1/2, right? Whatever. What's the probability of failure? 1/2. It's the complement of that, right? Does that change from trial to trial, or does that remain constant? Yeah, it doesn't change. Every single time you flip a coin, it's still 50-50. Okay? Rule number 4, the trials are independent. What do we think? Does the first coin toss affect the second coin toss? No. Are they independent from one another? Yes, so they are independent. We're good with that. And then the 5th rule, the binomial random variable is the count of the number of successes in trials. So this said, toss a coin 4 times and record the number of heads. Is the number of heads in 4 tosses a binomial random variable? So the binomial random variable is the count of the number of successes. Well, my question is, how many possible outcomes do we have if we are tossing a coin 4 times? You guys remember how to do that? Very good. 2 to the 4th equals how many? 16 outcomes. We have 16 total outcomes, right? That ranges from heads, 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 all the way down to tails, 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 tails. Now, we could sit here and list all of them out, but I already have that for you in this table right here. So for part E, we're going to put C table. So that means this is a binomial random variable. So I want you guys to look at this. These are all the possible outcomes for tossing a coin 4 times. Okay? Those are all my possible events, from tails, 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 tails to heads, 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 heads. Okay? Now, we want to track the number of heads that we could possibly get. So my first option is I could get 0 heads, which means I tossed 4 tails. Okay? The probability of getting that is 1 out of 16. And then here, if I got 1 head out of the 4 flips, there are 1, 2, 3, 4 possibilities where that can happen. So there's my probability. Do you guys understand how this table works? Okay. Now, what we would call this guy right here, the number of heads, that's my random variable. That's going to be x, and the probability is going to be the probability that capital X equals x, or just the probability of x. You guys know that that's the same thing. Okay? Now, when you have a table, it's really nice because you can, like, list all of those possible outcomes, and you can figure out, like, how many have 0 heads, how many have 1, how many have 2, how many have 3, and you can organize it, and you can see clearly what the probability is going to be. But coming up with this probability distribution is a lot more tedious than in the past, as 4 tosses of a coin produces more results. When we had 3 tosses of a coin, we could easily organize those 8 outcomes. Then we had 4, we could even easily organize those 16 outcomes. But what if we tossed the coin 10 times? How many outcomes would we have? 1,024, right? Or what if we tossed the coin 20 times? If we tossed the coin 20 times, we would have 1,048,576 outcomes. Would you guys have any desire to list all of those possible outcomes? No. So coming up with a binomial distribution for that, coming up with a nice little table with our probabilities would be a nightmare, okay? And it would be unrealistic. That's where the binomial probability distribution function comes in hand, all right? So the binomial probability distribution function looks like this. You guys have it on a little box there. It is a long, complicated formula, so it looks intense, but we know all of this information already. The first thing we need to know is when we have the combination of n choose x times, what does P stand for again? The probability of success raised to the power of x, which is the number of successes, and then we multiply that by 1 minus P. What was another way of saying 1 minus P? Failure, which is just Q. All right? So using this, instead of going all through this, let's use this over here to find what is the probability of tossing 3 heads out of 4 tosses. Before we even go on, we know the answer should be 4 out of 16 or 0.25, right? We know that. Let's see if we can use this formula to get there. So what is the probability of tossing 3 heads out of 4 tosses? So we need to know N, P, and X. We need to know all of this information to put it in this formula. So N is the number of trials. How many trials did we say we were going to have? 4. P was the probability of success. What did we already say that the probability of success was? 0.5, because there's tails and heads, 1 out of 2. And X is the number of success in the number of trials. How many heads do we want to get? 3. So those are my 3 possible, my 3 pieces of information that I need for this. Now I can put it into my formula. So I want the probability of 3 heads in 4 tosses. Okay? I'm going to move this up so you guys can see. 3 heads in 4 tosses. Now, that's going to equal, in choose X, so that's going to be 4 choose 3, times my p-value, which is 0.5, raised to the power of X, so to the power of 3, times Q. What's my Q value going to be? What's my Q value? If my p-value is 0.5, 0.5, it's the complement of that, right? Raised to the power of n minus x. So n is 4, x is 3. What is 4 minus 3? 1. So that's what we're going to do. And to type that into Excel, you're just going to do it all in one. So we're going to hit equals, and we're going to have combination of 4 choose 3, and then we're going to close that parenthesis, and I'm going to multiply that by 0.5 to the power of 3, and again I'm going to multiply that times 0.5 to the power of 1. And what should we get again? 0.25? Did we get that? Okay, so the probability of tossing 3 heads out of 4 total tosses is 0.25. You have a 25% probability. Now, this formula is long and it's messy. And yes, it is given to you on your formula card, on your formula table, but it involves a lot of thinking and it involves a lot of calculation. And it would be really nice if our Excel could do it for us. Okay? Do we need a second to catch up? Okay. Do you need me to click on it so you can see my formula again? Oh, there it is. Combination 4 choose 3 times 0.5. I wonder if I can double click it so you can see it bigger here. There you go. Now that's a lot of work. That's a lot of calculations. And again, you have that formula on your formula sheet, but it's a lot of thinking to make sure you get it right. So that's why Excel can actually do it for us. So instead of going through that whole process, we can use the binomial probability distribution function in Excel. And to do that, our function is going to read equals binom, B-I-N-O-M, dot dist, D-I-S-T, short for binomial distribution, and then you have to put in 4 different measures. And remember, when you start typing it in, it tells you what it wants. You just have to understand what it's asking. So when you type it in, it's going to ask for binom dist of 4 measures, okay? The first measure is going to be your x value. So if we're going to do it again, the probability of tossing 3 heads out of 4, what was my x value? My x value, oh, where did I go? My x value is 3. That's how many we want. Then we want my n value, the total number of trials that we're going to have. How many trials do we have here? 4. Next, they want your p-value, the probability of success. And what did we say the probability of success was? 0.5. And then the last value is very important. The last value, we want you to put false or 0, okay? This false just tells Excel not to accumulate your answer with all of the probabilities that come before it on the probability distribution. Here's what that means. We know this is my probability distribution for this problem, okay? By putting false, it tells me I only want this number, okay? If you put true or 1, it would give you the accumulation of this number and everything that came before it. So it would give you this one plus this one plus this one plus this one. Does that make sense? So false gives you just the one number, whereas true gives you that number and everything before it. Okay, so just keep that in mind. So that being said, let's use this function here to type it in. Okay, let's use this function here to type it in. So we're going to type in equals binom, B-I-N-O-M, dot dist, D-I-S-T, open parenthesis, and look, again, it tells you what it wants. The first thing is number of successes. So we want 3, comma. Then it says the number of trials. We said 4, comma. Then it says the probability of success, which we said was 0.5, comma. And then finally, look, it says true or false, cumulative distribution function or the probability mass. We only want the 1, so we want a false, or 0 works for false. Okay, 0 works for false. Okay, and we know that it should equal what? 0.25. There it is. Okay, now I'm going to make a note here just to remind myself that if I put true, then, or 1, then what it's going to do is going to give me the probability of 1 plus the probability of 2 plus the probability of 3. Okay? It's going to give me everything else below it. That just kind of helps me remember what the heck's going on. Okay, so now that we have an understanding of this probability binomial distribution function, let's do a couple of examples with it so you guys can see how it works, like what it is for. Okay? Give you a second to catch up. All right. Number 3 says, the U.S. Land Management Office regularly holds a lottery for the lease of government lands. Your company has won the right to 12 leases. Historically, about 10% of these lands possess sufficient oil reserves for profitable operation. Construct the distribution for the number of leases that will be profitable. What is the probability that at least one of these leases will be profitable? So from this information, we have to figure out 3 things. We have to figure out our N value, we have to figure out our P value, which will subsequently give us our Q value, and we want to figure out our X value. Okay? Now my first question is N. How many total do we have? How many? 12. They gave us 12 leases. Now the probability of success, we're saying success is that we are going to have sufficient oil reserves for profit. What's the probability that that's going to happen? 0.1, right? Now X, I'm going to leave blanks for a minute, because what I'm going to do is we're going to come over here and we are going to fill out this table in order to give us the probability for each one of these. Like, what's the probability that I'm not going to have any of them? What's the probability that only one of them are going to give me? Does that make sense? Now, one thing you need to understand is that when I have 12 total trials, when I have 12 random variables, I actually have 13 in my table, because there is still a probability that none of them will be successful. So when you have an n value of 12, you're going to have 13 x values because you also have to put in 0. The same thing when we were flipping a coin 4 times. If you'll notice in that table, there were 5 possibilities. There was getting ahead 0 times 1, 2, 3, or 4. Does that make sense? So here, what we're going to do is we're going to go in this probability column, and we're going to use the binomial distribution function. So we're going to say binom.dist. And again, we're going to do open parentheses, but be very careful here because the number of successes, which is my x value, is going to be dependent on which row I'm focusing on. Now, I don't just want to type in the number 0 because I want to make it easy on myself. I want to make it something that I can just drop down and it'll fill out, right? So what I'm going to do for the number of successes is I'm going to come over here and just click on this cell. Okay, I want the number of successes to be whatever number is in that cell. Then the rest of it I can fill out. So the rest of it I can go, comma, we have 12 trials, comma, the probability of success we said was 0.1, and then comma, cumulative, again, is false. I don't want it to accumulate. I only want the probability for that one number. All right? Then I'm going to hit enter, and you should get 0.28-ish. Okay? Now what you're going to do is you're going to click on that, and you're just going to drag it down to auto-fill in for the rest of that table. Now, if you'll notice, the probability for each one, the probability that you'll have 1 goes up a little bit, 2 then starts to go down, and then from there it steadily decreases until it's almost 0. But to make sure we did it right, I'm going to come down here, and I'm going to take the sum of it. And the sum of all of these should equal what? They should equal 1. And if you did it right, it should equal 1. Now notice, sometimes it might be like 1.00001, or it might be like 0.99999 because there's like a little bit of rounding error in there, but that's okay. As long as it's close to 1, we are good. All right? Now, the question was, what is the probability that at least 1 is profitable, right? Okay? At least is a phrase that means which symbol? Greater than or equal to 1. So we're really finding the probability that it is greater than or equal to 1. Okay? So what we're going to do is we're going to hit equals. And I want the sum of all of the probabilities starting with what number? 1. And I'm going to go from 1 all the way to 12. And you should get about 0.72. Good? Okay, so again, to get that guy right there, I took the sum of all of these guys, and that was the probability that it was greater than or equal to 1. Okay, so again, what is the probability that at least one of the leases will be profitable? 0.72, about 72%. So that's not terrible odds. It's likely that it would happen. Now, the next thing we need to talk about is that there was another way we could have found this. Once we had the table, we could have also used the complement rule to find the probability that at least one of the leases would be profitable. Because the complement rule says, hey, if it's going to be at least 1, that means it's not going to be 0. So I could have come over here and I could have just said equals 1 minus the probability that none of them would have been profitable. So I could have just said the probability, or equals 1 minus the probability of 0. And that should give you the same value. Okay? 1 minus the probability of 0. So understanding what a complement means, understanding what these words are giving you helps you find these values in different ways, some of them easier than others. Because if it said like greater than or equal to 4, the complement rule probably wouldn't have been good because you would have had 1 minus like a bunch of them. But when it's greater than or equal to 1, there's only 1 that's not included. So using the complement rule just takes 1 minus that one cell instead of finding the sum of all the rest of them. Okay? All right. The next thing that we are going to talk about is how to find the expected value of a binomial random variable. Now remember, the expected value is really close to the average. That's another word for average, so it's the mu. Now if you want to find the mean, the average, the expected value of a binomial random variable, all you have to do is take your n value, so the number of trials, times your p-value, the probability of success, okay? Now the variance and the standard deviation of the binomial random variable, I'm having a great day, of the binomial random variable are very similar. So to find the variance of this, you take your n value times your p-value, and then it says times 1 minus p, but we know that's the same thing as your n value times your p-value times your q-value. That's how you're going to find the variance. And then the standard deviation is just the square root of that. So the square root of n times p times q. Okay? So let's try that because it really should be quite simple. So over here it says find the mean, variance, and standard deviation for the problems from number 3. And I've already brought down that information that you want. Now, you have a couple of options here. You could literally just type it in if you want, or you could come over here and put n is 12, like 12, and then 0.1, and then the complement in these boxes, so that you could just use cell references. It's up to you. So to find the mean, it says we want my n value times my p value. So that's going to equal, what is my n value? 12 times what is my p value? 0.1. And that gives me an expected value of 1.2. That means in the long run, about 1.2 plots will be profitable on average in the long run. Okay? Now to find the variance, we need to take my n value, which we said was 12, times my p value, which we said was 0.1, and then we need to multiply it by my q value. The q value is the probability of failure, which is the complement of success. So if my success, my p value is 0.1, what is my q value? 0.9, right? It's just the complement of it, 0.9. And you should get 1.08. Did anybody not get 1.08? Okay, then the standard deviation, you could type it in. You could go square root of 12 times 0.1 times 0.9, or we could just go equals square root of, and then I'm just going to click the cell with my variance in it, because I already have the variance. Why would I type it in again? I'm just going to go the square root of that cell, and you should get approximately 1.04. Good? So if you want to use the numbers 12, 0.1, and 0.9, you have to retype them in a cell without the variables. Okay, so let's look at number 5, and let's solve it using the information we learned today. So number 5 says, a certain insecticide kills 70% of all insects in lab experiments. A sample of 10 insects is exposed to the insecticide in a particular experiment. Okay, so I just want you to think about the sentence that we just read. An insecticide kills 70% of insects it comes into contact with. So they took 10 insects and they made contact with it. How many would you expect to die? 7 of them, right? 70%? Now, what is the probability that exactly 3 insects will die? So we just logically thought through this problem. We said we think 7 insects should die based on this information. They want to know what's the probability that only 3 will die. Do you think this is likely or unlikely? Unlikely. So just keep that in mind. Let's see if it's true to what we think. And it says round your answer to 4 decimal places. So to do this, we have to see if it is a binomial experiment. So my first question, are there 2 outcomes on each trial of this experiment? Is there a success and a fail? Yes, they die or they don't. Very good. Is it consisting of identical trials? Is every single trial the same? Yes, we're not changing anything. The probability of success, do we have a probability of success here? What is it? 0.7, very good. And then are the trials independent? Yes, it's not going to affect if one bug dies if the other one does or does not. And then the binomial random variables account of number of successes. So let's see here. We are going to find an n value. So how many total trials are we extending this to? 10. We have 10 bugs that we're going to do it to. All right? And let's go with my probability of success. We said was what? 0.7. Very good. And then my x value is how many successes. I want how many bugs to die here? 3. This is a really morbid problem. Super morbid. All right. So we have our values. Let's type it in. So I'm going to go equals binom.dist. And we can put in all of that information. The number of successes we said was 3. The number of trials we said was 10. The probability of success was 0.7. And again, we want 0 or false. We don't want it to accumulate. We only want exactly 3. Okay, we only want exactly 3. And what do we get? 0.009. Were we right? Is this unlikely? Yes. The insecticide that they're creating, it's too successful for only 3 insects to die. If only 3 insects were to die, I think the scientists would be like, I think we found a new species and we need to call someone because these are super bugs here. Okay? All right, let's look at number 6. The magazine mass marketing company has received 16 entries in its latest sweepstake. They know that the probability of receiving a magazine subscription order with an entry is 50%. What is the probability that no more than 12 of the entry forms will include an order? Round your answer to 4 decimal places. So what do we think? Is this a binomial probability? So like, is there only 2 outcomes, success and failure? Yes. So what is the success here? You get an order, and the failure would be you don't get an order. Okay, so we want to fill out my probability table because it says what is the probability that no more than 12. So we're going to have to accumulate some here, right? So we need to figure out my n value, my p value, and my x value. Here I'm going to do it actually all on the computer so you guys can see how to use cell references. So we're going to have my n value, my p value, and my x value. Okay? So my n value, how many total do we have here? 16, very good. What's the probability of success here? 0.5. And then my x value is really only for me to know because we're going to put all the x values into my actual table. But my x value is that it says no more than 12. What is no more than as a symbol? Less than or equal to. So I'm going to go Control U for underline. Control U for underline. Then I'm going to click the less than. That gives me less than or equal. Then I'm going to go Control U to get rid of the underline. And I'm going to type in 12. Less than or equal to 12. All right. Let's come over here and fill in my table. So we're going to have equals binom.dist. The number of successes is going to be my x value. Click on that cell. The number of successes is going to be my x values. Click on that cell. Comma, how many total trials did I have? 16. Comma, what's my probability of success? 0.5. Comma, is it cumulative? No, false. Then you're going to click and drag it down so it fills out your whole table. And I don't like that bolded, so I'm going to unbold it. Is that the right word? Probably not, but I'm going to go with it. Now, the probability that I am going to be less than or equal to 12 is going to equal the sum of what? What am I adding up here? What am I adding up here? From 0 to 12. Very good. All of those from 0 to 12. Because it's less than or equal to 12. All right. Now, to do it like this every time is more than okay, and I encourage it. But if you are very confident in this and you're like, man, I got this, you can use the true value. This is not required. You are welcome to use the table. If the table makes sense to you, stick with the table. But if you're like, hey, true, if I type all of this binom dist, and then instead of putting false, I put true, I know that it's taking that number and it's adding that and all of the ones below it. You could do this. You could go binom.dist, and for the number of successes, you would still put 12. The number of trials, you would still put 16. The probability of success would still be 0.5. But for cumulative, you could put 1 or true. And what that would do is that would take 12 plus 11 plus 10 plus 9 plus 8 plus 7 plus 6, 5, 5, 4, 3, 2, 1, 0, all the way to 0, and you should get the same thing. So if you understand the concept of true and false, you are welcome to use that. But if you're like, no, thank you, that makes no sense to me, use the table, because I know that you have a firm understanding of the table and that you can say less than or equal to 12 is the sum of all of these. That is more than okay. But if you're like, I've got it, you're also welcome to use the true value. Okay? All right, your homework is on hot.